basically is about optimizing an implicit and unstructured code on many and multi-core HPC architectures. And I'm insisting here on the unstructured computations and on the many and multi-core HPC architectures, mainly on the many into Xeon Phi. And most of the slides here will be talking about into Xeon Phi, and then the multi-core, we're targeting the Skylake architecture. I came from KAUST, from Saudi Arabia. So my outline for the talk is, basically I will speak first about the application, which is fully unstructured Navier-Stokes in 3D. And I'll talk about the architecture, which is basically we're targeting into Xeon Phi architecture, and later we extend it to Skylake. I'm going to talk about the algorithmic and architecture-specific optimizations, evaluation and result, and then I'll conclude with some remarks, and then the ongoing work. So let's start first about the application. Funny 3D, or fully unstructured aerodynamics code. It is an unstructured tetrahedral mesh Euler code to solve Navier-Stokes equations. It is a research code that was started initially by NASA Langley Research Center, and it's still the state of practice at NASA. For over 2 decades, Funny 3D has been under active development for modeling fluid flow, design optimizations, aeroplanes, automobiles, and submarines with vertices approaching the billions. Our code is a fork from the original Funny 3D. It's called Betsy Funny 3D. Let's look at the history of the code. So Betsy Funny 3D development started by Professor Keys and Dinesh Kaushik and Barry Smith back in 1995. From 1995 to 1996, they experimented single program, multiple data, or multiple instruction, multiple data parallelism in the form of MBI, where they ported the code into Betsy and they implemented the unstructured computations in Betsy. This code in 1999 won the Gordon Bell Special Prize. And then in 2001, there was a special experiment on parallel I/O, experimenting MBI I/O. In 2005, they experimented adaptive linear solvers, where at every time step they changed the linear solver based on some input parameters. From 2009 up to now, the code is being experimented within a single node. We're trying to optimize and scale this code in a single node architecture. So in the beginning, it was starting on IBM Blue Gene B, where they tried to scale it within at most 4 threads per core. And then in 2015, they experimented Sandy Bridge and Ivy Bridge with up to 20 cores per node. And we experimented on KNC, Haswell, and Broadwell in 2016, and now we're working on KNL and Skylake. The architecture, I'm not going to spend time because most of you know KNL, but the most important thing that I want to insist here is that our target here is we're doing a hierarchical partitioning, where in the beginning we target to first populate the DRAM, and then the MC-DRAM, and then populating the core, the tiles. We're targeting the L2 caches between the 2 cores, and then we're populating the L1 cache within a core, and then later on populating the register, the 512-bit register. So this is how our optimizations goes. We start from the higher level, from the memory, all the way down to the registers. The algorithmic and architecture-specific optimizations. First, let me explain from computer science perspective, what are the main or the hotspot of the computational routines of Betsy Funny 3D. So in the beginning, so if we divide the code into generic, we can say we have a setup phase and the Newton-Krylov-Schwarz algorithm phase. So the setup phase, basically, we are reading a binary mesh file. We try to manipulate every subdomain separately, and then we order the workload, we partition them, and we allocate them based on the workload peer threads. The main kernel, or the most important kernels, are the Newton-Krylov-Schwarz algorithm kernels, where it's basically an implementation of the implicit parallel algorithmic framework. We are relying on linear algebraic kernels and some callbacks to Betsy. Our target here, we're not optimizing Betsy, we're optimizing the callbacks to Betsy solver, which is the physics of the problem. So the linear algebra is handled through Betsy, and we call Betsy as a black box. We don't touch Betsy. We mainly call GMRIS and ILU within a single node, but when you go to the larger scale, we have GMRIS, Schwarz, and ILU. For the edge-based loops kernel, which is the main of our target, we have 73% of the entire runtime is being consumed by the edge-based loop kernels. Our target is to optimize the flex evaluation, which is the most time spent at the kernel evaluation, the preconditional construction, and the pseudo time steps. The flex evaluation consumes in excess of 50% of the overall time, so that's why most of our optimization are devoted for the flex kernel, and it's actually the most complicated kernel. So when we look at the pre-processing and setup phase, although it's not consumes much of the code, but since we are running on KNL, so we rather have like embarrassingly parallel code so that we can get the best out of the KNL. So for the setup phase, we perform a single I/O operation in the beginning of the code that read the whole mesh file into the memory. Of course, we're getting benefit because the mesh file can fit into the memory. If it doesn't fit, then we do a partitioning for that. And then later on, there is a low-level parser that manipulates every mesh component independently. So every mesh component are being manipulated independently. It's a task-based parallelism where we basically sort the data and then later on allocate it into memory. So these two phases are fully parallel using OpenMP, task-based parallelism through OpenMP. The stream buffer parsing phase is because the mesh file is stored in big Indian format, like Linux format, so we do a byte-by-byte swapping to make it a little Indian format because the application handles a little Indian. Optimizing the edge-based loop kernels. Here we are insisting to do two way of optimizations. The first one is data level parallelism, and the second one is thread level parallelism. But before that, we need to adjust the data structure and the data accessing layout to be vectorization friendly. So in the beginning, we did a data layout transformation where we used basically the most well-known for vectorization friendly structured arrays. So the geometric informations, including the edge information, the nodes information, the data information, all of them are being allocated in a struct of multiple arrays format. For the residual and the gradient vectors, we first look at allocating struct of arrays of structs. Where every struct element has an array of the size of the vector length. However, since we know beforehand that we have 4 degrees of freedoms per node, then we need at every time step to evaluate four values, the residual and the velocity, next to each other in the memory. So that's why we somehow manipulated the structure of array to become structure of strided arrays, where we have a stride of 8. These 8 constitute of 4 degree of freedoms aligned next to each other. So every time step we fetch 2 edges, and these edges represent the 8 components. We order the endpoints of the edges in ascending order so that we improve the locality of reference. So basically, when we process one endpoint, we know for sure that is this endpoint will be processed all of the endpoints that connect to the same edge, and then moving accordingly. So this is improve the spatial and temporal locality of the memory. And then finally, we order the edges to distribute it across the threads. We don't handle this through a runtime. What we implement a manual distribution, considering like if we do a large an MBI distribution where every nodes compute their own subset, and then we do redundant computations per thread. So we use meters to partition the grid across the OpenMP threads, and then for each OpenMP threads to eliminate the communication between them, so there will be no core-to-core communication. We have a redundant computations within every core, and then we reorder this data to reduce the sparsity through reverse cut-Helminki. So when we do a reordering and third partitioning, the main kernel loops that loop over the edges looks like this. First, every thread is basically loop over their own subsets to the next threads, and then everyone loads and compute their own subset, and then if the data belongs to the first node of the endpoint of the edge, then the threads will perform a write back to that specific node. If the other nodes as well is processed by the same edge, it perform another write back to the same node. So that in here, one of these will be occur like redundant computations. These two if condition has been eliminated later on with the vectorization. So also because we are running on KNL, so we say, okay, let's optimize the code to be also an MCD-ROM friendly. So instead of relying on NumaCTL to allocate the MCD-ROM, we decide, okay, let's consider part of the the data that's being processed at every time step will be in the MCD-RAM, so we can access them in the fast manner. And the data that we don't touch them frequently will be in the DRAM. So for that, we use the high bandwidth POSIX mem-align that's been implemented in memkind library of Intel, the open source library. And we provide the page size for that with alignment of 64 bytes. And then at every loop, there are some leftover loops that loop over the mesh boundaries. So these are not, they don't consume much of the time, but they have like, if you're running in KNL and if you run them on single threads, the time gets a bit worse. So that's why we also partition this. But with our partitioning, we use like an edge coloring algorithm that I'll explain later, where basically color every triangle faces, and then we loop through these triangular faces within a color, and then we basically perform the computation. So with this thread partitioning for the boundaries, the loop looks like this. It's basically we loop over every color, and then within the color, and OpenMP threads can operate safely because within every color, the data is local to a specific thread. So one of the important parts of KNL is the vectorization, the 512 vector units. And this is what most of the time we invested to vectorize the code. As I said, the Flux kernel is very complicated kernel. So the compiler normally fails to vectorize this code due to the dependency, the unstructured nature of the code, and it's very huge computation, arithmetic computations within that kernel. We tried to vectorize it within 70 pragma, but the compiler fails as well to vectorize it. So hence, we moved to 100 vectorizations in intrinsics. I know this is not a well-recommended techniques because the code is not portable, but thankfully that is the AVX512 is supported in Skylake, so we managed to port it in Skylake with a very little of modifications. So the data level parallelism, before I go and explain what we did, is the AVX512 is introduced in KNL. KNL and Skylake, both of them support the AVX foundation, which is the main instruction set, and the conflict detections. These two are the most important instruction set that we use in our vectorization. For KNL, we have specifically the exponential and reciprocal square roots. These are also two instructions we utilize for KNL, and for Skylake, we transfer them to be Skylake friendly. And we utilize also the prefetching instructions that are implemented in KNL. For Skylake, they have the VL, the vector length, and the double word and quad word, and the bytes and word instruction, which is basically 16-bit, 32-bit, and 128-bit support for instructions. Now, how do we vectorize our code? So in the beginning, we use normal intrinsics for loading the data from the main memory to the registers using a load where the data are aligned next to each other. For the unstructured or for the indirectly addressed data, we use a gather instructions. We perform several gather instructions to load these data. And also we utilize the AVX512 gather instruction that's implemented in KNL and as well as implemented in Skylake. For the arithmetic operations, all of our operations being adjusted to be fuse, multiply, add. So we don't have like a single multiply or a single add or a single division. All of them are fuse, multiply, add, and there's no division at all. So we utilize VM add and VM subtract and V negation for add if you have a negation value. For the control, we also for the condition, we transfer the code from the control flow to a data flow conditioning through masking instructions. So every conditions or if conditions there is being transferred to a mask operations. For the square root and the division, we make them as reciprocal instructions because the division and square root are very expensive. So, for example, in a square root of x, we multiply the x value with the reciprocal square root of x. For the division, we multiply the reciprocal of x times c, which is the c bar t. The prefetching instructions at every kernel launch, we do a prefetching to prefetch the next data set that will be operated in the next iterations, so that we populate L1 cache to be ready for the data to be processed in the next instruction. If the L1 cache is already populated, then we populate L2 cache based on the time. And then finally, for the write back operations, we do a conflict detection with scatter instructions, and I'll explain this. So, for the we did the whole calculation operations was totally an intrinsic mode. But when we do the write back, we do it sequentially. So at every kernel launch, we do 8 times write back because there was no conflict detection. But in the AVX 512, thanks to the conflict detection, so in the worst case, we'll do 8 write back operations. But this is in the very worst case. And also this one, we did a remanipulator for the data, which I will explain later, how we reduce the number of the rewrite back operations, the most inner loop. So, in brief word, how we did is basically we scan the assembly lane to identify the conflict data. We generate the mask. This mask separates the conflict and non-conflicted data. We perform a safe write operations based on the mask, and then we perform a SMD Boolean operation to remove the already written data from the mask, and then we repeat the steps again till we make sure that the SMD has been, the SMD lane, all of the data in the SMD lane has been written. So in the worst case scenario, this will be repeated 8 times, but this is in the very worst case scenario, this will never happen. In the average case scenario, this should happen like 3 to 4 times. So this is an example for our vectorized loop that I showed earlier. So this is within every thread. So as for every thread, we fetch 8 data that populate one vector lane. And then when we do the write back operation, we have a very inner loop that this loop first calculates the mask indices in the beginning before entering the loop. This is the calculation is based on the thread ID. And then we compute the conflict within the vector. And then we broadcast the conflict data to vector to perform to test the vector whether there are conflicts or not. And then once we test the vector and we create the mask that is conflict free, we gather the operation. We perform gather, compute, and scatter operations, and then we perform XOR operation to remove the already written data, and then we repeat the loop again. So as I said again, this at most should be executed 8 times. But this is in the very worst case scenario. In the average case scenario, it should be executed 3 to 4 times. And then we did a remainder loop where we just basically loop over the remaining values of the vector. I mean, this should be like maybe 4 to 6 times. So, as I said, is there a way to do it before relying on the conflict detection instructions? To improve the vectorization, we invented a technique where when we do the reordering operations and the pre-processing step, we take into consideration a third level of partitioning, which is across the vector lane. So what we did basically is we implemented a bucket sort that's based on variant of edge coloring. So this bucket sort extract an 8 elements for every thread, extract 8 elements, and try to make sure that every 8 elements are adjusted next to each other that are conflict free. Of course, this is, cannot be, it doesn't happen all the time because at the end you are limited with the size of the mesh. But as the problem size gets larger and larger, then you can extract larger 8 independent edges within a bucket. So this is like a sketch for the edge coloring. It's basically we did a bitmap. So for every thread, they have a bitmap for their located data, and then we first set the bits, and we check if these 2 bits, the 2 endpoints are being colored. If yes, then we move to the next bit. If no, we make sure that we are within the 8 buckets. This is very important because if we don't make sure that's within the 8 bucket, then this reordering will screw up the first ordering that we did for the spatial and temporal locality within threads. So we just restricted within 8. And then we swap them, we reorder them again, and then we keep looping until we pass through all of the mesh